Welcome everyone. So we're going to start our lecture on integrals. Objective integrals. Well, so let's begin by asking a question. How do you find the area? Question. How do we find the area? Okay. So depending on the object that we have, we follow some formulas. Suppose we have just a rectangle. You have x-axis, you have your y-axis, and you're going to just fit this rectangle here. There you go. So suppose the measurement here is L. The measurement here is W. So you say that, hey, the area of this object here, the area is equal to this measurement times this measurement, and here I have my formula. Okay, there you go. But if I give you something like this, what if I have my x-axis, then my y-axis, and then I have this function here. This is the function that I have. And I ask you, hey, what is the area below this graph bounded to x-axis? What is this area? Now, how do I calculate this area? See, it's not as easy as calculating this area. Why is that? Because this function, for example, y equals to f of x, is changing. F of x. This function on top is changing. Well, okay, how do we find this area then? One method is to divide up your x-axis into small intervals, sub-intervals, and then after finding those little measurements, multiply them by the height, your y values, and adding these small areas together to come up with an approximation of this whole area. So I say that it's pretty smart. One way, one method is to divide up the x-axis into sub-intervals. Then calculate the areas, these small areas over these sub-intervals. Finally, add them all together. It might not give us the exact or precise area, but it gives us a good approximation. Well, now I expect you to ask, okay, this is just an approximation. What if I need the exact value? What should I do? Well, to find the exact values, instead of using approximation, we're going to introduce the concept of integral. Well, before defining the integral, we need some introduction, some backgrounds about Riemann sum, and then we're going to take the limit of the Riemann sum and introduce the integral. Well, let's go over one example, then we generalize the idea. Example. This example says, well, estimate the area under the parabola y equals to x squared from 0 to 1, 0 to 1. Okay, estimate the area. So let's take a look at the graph first. This is our x-axis. This is our y-axis. Okay. And parabola y equals to x squared, 0, 0, 1, 1. This is my parabola. Okay. Since the question says, hey, estimate, what I'm going to do, I'm going to divide off my x-axis into sub-intervals. So I'm looking for this area. What is this area? What's the approximation of this area? So let us divide up the x-axis. Between 0 to 1, I'm going to divide this guy up into, let's say, 4 sub-intervals. Totally up to you. We can have as many sub-intervals as you want. You might say, hey, I want to have 2 sub-intervals. Absolutely fine. So what are we going to do? We're going to take 0 to 1, a half, going to have a fourth, and 3/4. So now, what do we have? This is my parabola on top of it. And then I'm going to divide these guys up into small rectangles. Small rectangles, okay. Well, this is the first rectangle. The second rectangle. The third. And the fourth. What I'm going to do, I'm going to calculate each of these areas add them together and get a nice approximation for this area. So S1, S2, S3, and S4. S1, S2, S3, and this guy is S4. S representing the area of each of these rectangles. S1, the area of the first rectangle. Okay, isn't that hard to find the area of rectangle? I need this little measurement, this little piece here, and I need this measurement for here and here. It doesn't matter. So I have a 4 times a 4 is on x-axis. On y-axis, I get a 4 raised to the second power. A 4 to the second. This is going to be the area of the first rectangle. A 4 times a 4th square. This is this little area here. So let me just show you. This is 0 to a 4. And here you have your length here. This little measurement here is a 4 raised to the second power. So this length times this length, a 4 times a 4 times a 4. S2, the area of the second rectangle. Okay, the second rectangle is a 4 to a half. Four to a half. And okay, now I'm looking at this a little bit smaller than the second one. So it's going to be larger than your previous rectangle. So as you can see, the length is getting a little bit higher. So I have a half, my x is a half, my y is equal to x squared. So a half times a half. So this length here is a half squared. Okay, half squared. So the area, so here you have a 4 times a half square. We keep continuing this process. Now we need to find the area of S sub 3, then S sub 4. S sub 3 and S sub 4. For S sub 3, again, the length is a 4, but its height. So what do we have here? If I use 3/4 and use it as my x value, I get 3/4 to the second power. So a 4 times 3/4 to the second power. The area of the third rectangle, and finally the area of the last rectangle here is a 4. Now you have 1 raised to second power. Okay, so the area is now approximated. So for approximation, instead of using equality, we're going to use this symbol or double tilde. It's going to be the sum of S1 plus S2 plus S3 plus S4. We're going to add all of these together. Okay, approximately, we're going to get 0.4688. So the area is approximately 0.4688. It's not the exact value. It's just an approximation for the area. What are we trying to do? We're trying to use a method that Riemann represented to us. Riemann sum. Okay, so this method is part of the method that Riemann has used to approximate the areas. You might say, well, so far you took these rectangles that cover more of the area. Why you don't use rectangles that cover less of the areas below the curve? So you might say, hey, let us divide this guy up this way. Let's say, hey, this is our x-axis, 0 to 1, and then I'm going to again divide this up into 4 sub-intervals, but instead of covering the upper area, I'm going to start approximating the area using rectangles inside or below the curve. So now your first rectangle is going to be just here. Your second rectangle is here. Your third rectangle is here. And your fourth rectangle is going to be just here. So as you can see, now we're approximating the area using smaller values, smaller areas. So this guy is S1, area of the first rectangle, which is 0. The area of the second rectangle, the area of the third rectangle, and the area of the fourth rectangle. It's another way to approximate the area. Of course it is. But it gives you smaller approximation. So in this case, you can find the area of S1. So the area of S1, so the length here is a fourth. It's a fourth, but as you can see, the y value is 0 squared. 0 squared or just 0. S2, the area of S2 is going to be a 4. Now, this y value here is a 4th square. So, a 4th square. The area of S3, again, the length is a 4. Now you have a half raised to the second power, a half squared. And area of S4 is going to be a 4 times 3/4 to the second power of your y value. 3/4 to the second. Okay, again, you can add these areas together to find an approximation for the area of your area below the curve. So it's going to be S1 plus S2 plus S3 plus S4. Approximately, this area, smaller area, is going to be 0.2188. Okay, so what's the meaning of that? It means that this area is going to be in between 0.21, 88, and what was the previous number? 4688. But okay, this is an approximation, estimation. But what is the exact area? That's the question that we try to answer. Well, what they say instead of taking smaller areas or larger areas, we can take the middle points, midpoints here between 3/4 and 1. We can find the midpoint and find the y value, then find the midpoint, find the y value, find the midpoint, y value, midpoint, y value, and then add those up together. Again, using a midpoint gives us another approximation. Well, the next thinking is, why not dividing this into 8 subintervals? 64 subintervals? Let us increase the number of these subintervals until we get a very small length for these subintervals. What are we trying to do? We're trying to find the limit by making these very small. After finding the limit, the Riemann sum converts into a new concept, integral. So this is our next stop, talking about the integral. So let us wrap up Riemann sum this way. So the steps that we take from Riemann sum to go into integral. Suppose y is equal to f of x and x is bounded between a to b. The area of, let's just find the area below the graph of y equals to f of x bounded to interval AB can be calculated this way. Area A is equal to the limit of what? Limit of R sub n while n approaches infinity, which is equal to, we're going to write down the definition of Rn, Riemann sum, which is the limit of. Here we have f of x1 times delta x plus f of x2 times delta x plus f of x sub n delta x while n approaches infinity, and delta x is b minus a divided by n. A is equal to the limit. So this is the sum. We write this sum this way. Sigma f of x sub, can use I, delta x, I starts from 1, goes to n, n goes to infinity. Area A is equal to limit of sigma. What is sigma? This is sigma, which means addition. It's summation. Summation of f of x1 times delta x. What is delta x? Is b minus a divided by n plus f of x2 times delta x. b minus a divided by n plus the rest of the terms as n goes to infinity. Well, as n goes to infinity, this fraction is getting smaller and smaller. But what is delta x? Delta x is these little sub-intervals in x-axis. This is your parabola, the one that we used to approximate the area. Suppose it's bounded on x-axis between A and B. So delta x is those small subintervals. These small subintervals. Then f of x1, it gives you these y values. F of x2, f of x3, f of xn. So what are we trying to do? We're trying to make these sub-intervals very small by defining delta x. Then we take the limit of this sum, take the limit of the summation of this multiplication. This is y times x. These are these small areas. These are small areas. When you take the limit, while n goes to infinity, the limit of sigma converts into an ugly s, which we call the integral. So this is equal to, this is equal to the integral. So the limit of sigma is now the integral f of x, delta x is now dx. So dx is the limit of your delta x. And your x is in between A to, from Riemann sum to definite integral to define the area. Very well. So we're going to just go back and forth between some examples, techniques of integrations, properties of integrals, and the theorems. So I expect you to ask, well, now that you define this new symbol, how do you find the area of the parabola? Okay, that's a good question. Remember that in Math 1A, you learned that we have the derivative of a function and the antiderivative of a function, the opposite operation. So we're just going to do Math 5.2 and 5.3 and 5.4. Just going back and forth between these three. Now I expect you to ask, find, not approximate, find the area y equals to x squared when x is bounded between 0 and 1. So first of all, the way that we write the integral is you have the integral of your function x squared dx. X is bounded between 0 to 1. This is your lower bound, and this is your upper bound. So this is the lower bound, the lower limit. And this guy is the upper limit. How do we find this integral? Again, in elementary calculus, you learned about the derivative. It is the opposite of taking the derivative. Let's write a recall for you. Recall in elementary calc, you learn that if you have x to the n, the derivative of x to the n is n x to n minus 1. Now, the antiderivative, this is the derivative of x to the n. Now we're going to talk about the antiderivative of x to the n. The antiderivative of x to the n dx, let's come up with the opposite operation. It's going to be x raised to n plus 1 divided by n plus 1. We usually add a constant of integration at the end. So x to the n, you take the exponent, you add 1 to the exponent, n plus 1, and you divide that by this new exponent. This is the antiderivative of x to the n. Xn derivative will reduce the power. Antiderivative, we add 1 to the exponent and divide by that exponent. Now, what if we have lower limit and upper limit? If you have lower limit and upper limit, it's going to be like this. Suppose I have a and b here, my lower limit, my upper limit. It's equal to b raised to n plus 1 divided by n plus 1 minus the lower limit raised to n plus 1 divided by n plus 1. N plus 1. So this is what you learned in elementary calculus. This is the technique that you just learned today. X to the n dx. The antiderivative of x to the n is equal to x to n plus 1 divided by n plus 1 plus c. C is called the constant of integration. When we are calculating the area that we call definite integral of x to the n dx, we just find the antiderivative, we plug in the upper limit, minus the antiderivative, we plug in the lower limit. Then we subtract these two numbers and we find the area or definite integral. So let us take a look at this guy here. I have x squared. My exponent is 2. Okay, exponent is 2. So it means that I need to add 1 to the exponent, the antiderivative.
Professor, can we pause for a second? There's someone that's stuck in the waiting room that needs to be let in. They got disconnected, so.
So first, let us find the antiderivative of x squared. The antiderivative of x squared dx is equal to. So the exponent is 2. So we're going to add 1 to the exponent. We're going to have x to the third divided by that this new exponent 3. Again, if it's not definite integral, we add a constant of integration to it. So this is our antiderivative. Now we are interested in finding the definite integral or the area. In this case, it is equal to the upper limit is 1. So I'm going to plug in 1. I get 1 to the third divided by 3 minus the lower limit is 0, 0 to the third divided by 3. Okay, here we go. 1 to the third is going to be 1. I have a third minus 0 or a third. This is the area below the graph of your parabola bounded to 0 and 1. This is my x-axis and this is my y-axis. This is your parabola bounded between 0 and 1. And the area, this area here, is equal to a third. 1 over. By using the concept of integral, in this case, definite integral, we were able to calculate the area below the graph of our parabola, and x is bounded between 0 and 1. This is the very first technique that we learned in this class. So let us practice a little bit more. Here, I'm going to work with the same function, same parabola. And now I ask you to find other definite integrals or areas. Find the area, y equals to x squared. When x is bounded between 0 and 2, b, x is bounded between -1 and 1. Now let's find these two areas. So let me just move this a little bit here. It doesn't matter if you have positive numbers, negative numbers. We have lower bound, we have upper bound, lower bound, upper bound. So this is our A. This is our B. A, B. In both cases, the antiderivatives are going to be the same. So we're going to follow the same formula, but in calculating the area, we need to make sure we substitute the correct lower limit and upper limit into the formula that we have. So this case is going to be the area, lower bound is 0, upper bound is 2, and I have my function x squared, and I'm taking the integral with respect to variable x, dx. Remember that again, dx is the limit of delta x and delta x is nothing but b minus a over n when you're taking the limit as n goes to infinity. You're making those subintervals very small. Okay. I already know the antiderivative of x squared. It is x cubed divided by 3. X cubed divided by 3. Now I just need to substitute the upper bound. 2 to the third divided by 3 minus 0 to the third divided by 3. Here I have 8 over 3 minus 0, which is 8 hertz. This is x cubed over 3 plus constant integration. Okay, what about the second one? Second one, my lower limit is -1, my upper limit is 1. Okay, let's think about this. Here, I'm just finding not the area, but the definite integral. Integral -1 to 1 of x squared dx. Let's see what do we have. Here I have x cubed divided by 3. So 1 to the third divided by 3 minus -1 to the third divided by 3. I have a third plus a third, which is 2 thirds. So the definite integral, or in this case, the area of the parabola bounded between -1 and 1. So this is my parabola. And x is bounded between -1 to 1. So this is equal to 2 thirds. I have a question for you. What if, instead of calculating, you see these two pieces are the same, the exact same area on the left and the right. What if I just calculate the area from 0 to 1 and multiply by 2? So these are the types of questions that you should be asking. If y equals to f of x is symmetric with respect to y-axis on the interval -a to a, then the integral -a to a of f of x dx is equal to 2 times the integral 0 to a f of x dx. So here I could say, hey, instead of calculating the area from -1 to 1, I can just calculate the area from 0 to 1, which is a third, and then multiply by 2, which is 2 thirds. Following a symmetric function over -a to a.
Excuse me.
Very well. So let us go over another example for you. have the sum or difference of some terms. If you have the integral a to b of f of x plus g of x with respect to variable x, you can break this down into the sum or difference of these integrals. You can find the integral of function f or term f, add or subtract the definite integral of function or term gx. For example, suppose I ask you to calculate this integral. The integral of x squared minus 2x plus 5 plus 5 dx. Suppose I don't ask you to find any definite integral, just find the antiderivative of this function here, which is a quadratic function. We have a quadratic function, which is the sum of x squared plus minus 2x plus constant 5. If you have two functions, you can break it down into the integral of each of them. Then add the answers together, final answers together. If you have three of them, we can break it down into three integrals. If you have four, we can break it down into four integrals and so on. So we are finding the antiderivative of this quadratic expression or the sum of these three terms. It is equal to the integral of the first term with respect to variable x plus the integral of minus 2x dx, and finally we're finding the integral 5 dx. Well, okay, I already know how to calculate the integral of x to the second power. The integral of x to the n dx is x to n plus 1 divided by n plus 1 as a constant of integration. This is not that easy because I have x raised to the first power. Remember that invisible exponent, it means that you have 1. This might be a little bit confusing because you only have 5. When you only have a constant like 5 and you don't see any variable, it means that that variable is raised to the 0 power. So you can write this as 5 times x to power 0 dx. Now you can just follow this nice formula that you learned. So this is equal to x to the second is now x to the third divided by 3 plus, this is just the coefficient. You're just going to copy down the coefficient, -2. You have exponent 1, remember that. You're adding 1, a new 1 to the current exponent. So you're going to have x squared divided by 2 plus 5 is just the coefficient. We're going to copy down 5. And then here you have x raised to 0 plus 1. So you get x to the first power divided by 1. We're going to add a constant of integration at the end. So this is called constant of integration. We're done with calculus part. The rest is algebra. So algebra says we can simplify this guy. Here you can write it as x cubed divided by 3 minus x squared plus 5x plus c. This is the antiderivative of this function.